Welcome to all. So let us continue with the another solution which is available for critical section problem. So we have seen that algorithm 3 solves the critical section problem for two processes. So based on the flag values or flag array, we are going to target two processes which can meet the requirements of three solution. It may be mutual exclusion or progress, or another one is bounded weighting, isn't it? So now the next thing is, now let us develop an algorithm for solving the critical section problem for n processes. So it is not just for two processes. So number of processes, how many number of processes which are running in the system, for those processes this particular solution will be applicable. This algorithm is known as a bakery algorithm, and it is based on a scheduling algorithm commonly used in bakeries, ice cream stores, deli counters, motor vehicle registries, and other locations where order must be made out of chaos. So when we are getting the order in the bulk, so how exactly we can deal with those orders. So that is the reason why this algorithm is named as bakery algorithm. This algorithm was developed for a distributed environment, but at this point we are concerned with only those aspects of algorithm that pertain to a centralized environment. So ultimately our work or our goal is to find a solution for the critical section problem. On entering the store, each customer receives a number. The customer with the lowest number is served next. Unfortunately, the bakery algorithm cannot guarantee that two processes, or in this particular example, in the case of real-time example, it can be considered as customers, do not receive the same number. In the case of a tie, the process with the lowest name is served first. That is, if Pi and Pj receive the same number, and if I is less than j, if that is the case, then Pi is served first. Since the process names are unique and totally ordered, our algorithm is completely deterministic. So this is one of the better idea we can say, because if the numbers are identical or numbers are same, then we can go for the name of the process, and we check that which one is smaller and which one is greater. Based on that, this particular algorithm will take charge. Okay. Now let us see the common data structures are. So again, you have one array called choosing, and which has the capacity to store n numbers, and one more is integer array, the number with the name number, and which has the capacity to store again n numbers. Initially, these data structures are initialized to false and 0 respectively. For convenience, we define the following notation. So there are some notations which you have to see for this particular solution. So these notations can be converted for the programming if it is required, but generally the ultimate thing is, based on this notation, we are going to take the next step. So notation is nothing but a comma b is less than c comma d if a is less than c, or if a equal to c and b less than d. So these many conditions has to be satisfied, or it has to be checked, and from a max function, so we are just checking a naught to a n minus 1, okay, is a number k such that k should be greater than a for I equal to 0 to n minus 1. So these are some notations and some conditions which they are going to check for this solution, so that even though there are n number of processes, this critical section problem has to be solved. So that is the thing. The structure of process Pi used in bakery algorithm, to prove that the bakery algorithm is correct, we need first to show that if Pi is in its critical section and Pk, where k is not equal to I, if that is the case, has already chosen its number, k is not equal to 0. Fine. So it is with respect to Pi and Pk. So if there are two processes where k should not be equal to I, that also one condition, and if it is already chosen, then k is not equal to 0. Fine. So these are the some of the ideas which this algorithm will say. So with respect to code, if you want to see, so there is a do while loop. Inside the do you have choosing array, and all the elements are, or I element, the whatever the choosing array, whichever the process you are actually targeting, that has to be set to true. And number array also should be assigned with the max of number 0 to number n minus 1 plus 1. So it is one notation. So the whatever the data we are going to get, out of which what is the maximum number, that number or that place has to be put to the number array. Next again, once you have done this, then again you have to convert your choosing array to false, so that you can run the next step. So for j equal to 0, j less than n, j plus plus. So then after that you have one while loop for choosing j. Okay, so based on for choosing a j, you have again one while loop, and after that you have one more while loop to check the number array, and you have to compare the number of j is equal to, so number of j is not equal to 0, and or there is an and operation. Based on, if both the conditions are true, then only you are allowed to move further. Number of j comma j and less than number of I comma I. So ultimately these areas or this code will push you to the critical section once it is become true. Otherwise you are going to initialize 0 to number of I position, then you are going for remainder section. Fine. This is the overall idea actually. See, if you ask me what exactly we are doing here, it is just a solution or algorithm which was developed to overcome from critical section problem. So I have already explained what you mean by critical section, and you can imagine how exactly this can be possible. Okay, so to overcome from those problems, these algorithms are developed. So programmatically in our system, actually OS, while developing operating system, the developers have already implemented all these algorithms, and they have set their own code, they have written their own code for the solution. But in our textbook they have given some set of basic idea of the algorithm, so that you can grasp the idea how exactly you can overcome from critical section problem if there are n processes in the system. Fine. So this is the thing. Now you have one more concept called semaphores. Okay, the solution to the critical section problems presented are not easy to generalize to more complex problems. Okay, so you would have understood by now. So after the explanation, if the students are, out of you, like, I don't know how many head counts are there in second BCA, but say for example there are 60 members. Out of 60 members, if 10 members are the students, those who think practically. If that is the case, you would be in dilemma that what exactly we are learning here, what is the solution, how exactly we can implement. There are so many questions which will be popping out in your the brain, isn't it? So some concepts are theoretical, some or hypothetical. Fine. Some concepts can be practical. Okay, there are the difference, but whatever the algorithms you have seen, those algorithms have already practically implemented in the operating system to overcome from critical section problem. But it is not easy, because it is not just easy, it is not efficient, it may not be efficient. Every time whatever the algorithms the developers develop, they may not be efficient every time, isn't it? So they have to think twice, or they have to get the alternative idea or backup idea, even though there are any issues with respect to the algorithms which was developed by the scientists. Okay, so that is the reason. So you have one more concept called semaphores, just to deal with the critical section problem. So to overcome from this difficulty, we can use a synchronization tool called semaphores. So it is a synchronization tool. Semaphores are nothing but synchronization tools. A semaphore S is an integer variable that, apart from initialization, is accessed only through two standard atomic operation, wait and signal. So these two operations are tagged with the semaphores, so that wait and signal, that is nothing but if based on these atomic operations, the system can identify that whether it has to wait or has to send the signal or pass the signal or transmit the signal from one end to another end. These operations were originally termed P, and V. So these things are required. So that is for testing as well as incrementing. So P is for testing and V is for incrementing. So these are the just a variable name. So if you are good with the programming, definitely you will be knowing that why you are giving some variable names in a problem or a program while writing while writing for any particular solution, problem, or for developing some applications. You know the importance of variables and you give some names to those variables for some operations, isn't it? So this is the thing. Now you can see the pseudo code. So it is nothing but weight of S. So weight of semaphore. S is nothing but semaphore, isn't it? Weight of S, inside the weight, so you have one while loop where S is less than 0. If that is the case, if that is the case, then you should be going for n minus minus. So this is a classical definition of a signal in the pseudocode signal S. So you are in the signal S, you just trying to increment the signal value S plus plus. Okay, modification to the integer value of a semaphore in the weight and signal operations must be executed indivisibly. So what is the meaning? So whenever you are having that weight and signal operations, it has to be executed. Fine. So that is when one process modifies the semaphore value, no other process can simultaneously modify that same semaphore value. It is just like a flag variable or a variable where this process can actually update or increment or update the value already stored in semaphores. Okay, so but the condition is simultaneously other process should not be using it. Okay, so that is the main thing. Now in addition, in this case of the weight S, the testing of the integer value of S is lesser than 0 if that is the case, and its possible modification is S minus must also be executed without interruption. So this is one of the concept where, see, based on the algorithm they have gone for explanation. So once if it is done like this, what should be the next step? So there will be some methods, or there will be some steps which has to be followed. The same thing they have given with respect to this particular algorithm. Fine. Now there is you can concentrate on usage. We can use semaphores to deal with the n process critical problem, section problem. The process share a semaphore mutex standing for mutual execution. Okay, initialized to 1 each process pi. So for each process pi, how exactly you can do it? So it is in the program code, set of code in the last, you can see later. But now second point is we can also use semaphores to solve the various synchronization problem as well. Okay, for example, consider two concurrently running processes pi with the statement S1 and P2 with the statement S2. If that is the case, suppose that we require that S2 be executed only after S1. If that is a condition, okay, so once after completing S1, if the S2 has to be executed, then we can implement this scheme readily by letting P1 and P2 share a common semaphore sync initialized to 0 and by inserting the statement. So that also possible. Exclusion, mutual exclusion, or understanding will be there between these things. So if you are going for semaphores, and you can see the check code, you can check the code S1, and after S1 you have signal of synchronization, then do. Inside the do you have wait for mutex, and once it is done, then you are going for critical section. After that, again you are coming to get the signals of mutex, and then you are allowed to go for remainder section. So this is how the program flow goes. Fine. Now this is a simple code snippet. Okay, now if you think of implementation, then a main disadvantage of mutual exclusion solution of a section and the semaphore definition. So whatever the definition they have given in the previous section, so what is the actual issue? They all require busy waiting. While the process is in its critical section, any other process that tries to enter its critical section must loop continuously in the entry code. That is obviously because if one is using it, one is accessing it, then other process has to wait. There is no other option as well. This continual looping is clearly a problem in a real multi-programming system where a single CPU is shared among many processors. Because when you go for multi-programming, if this case persists, or if this case considered, then there will be a problem with respect to performance, as well as for multi-programming also. Okay, now busy waiting wastes the CPU cycle that some other process might be able to use productively. So CPU cycles, wasting of CPU cycle means it is not efficient, because CPU should not be idle, and whatever the application or whatever the process you are running in the system, that has to be given with the CPU, and the CPU should be always active. Remember this, CPU has to be always active. Fine. To overcome from this need for busy waiting, so okay, before that, this type of semaphore is called as spin lock. So keep on waiting thing, or busy waiting, or keep on waiting, is called spin lock. Fine, you have to remember this keyword. Some keywords are can be asked in the examination, I don't know, but this is one of the important thing. The next thing is, to overcome the need for busy waiting, we can modify the definition of the wait and signal semaphore operations. So that also possible, operation or updating or modifying thing also possible. When a process executes the wait operation and finds that the semaphore value is not positive, it must wait. Okay, if the value is not positive, something has to be wait. That is the reason why in the algorithm you have checked the condition like s is less than 0 or not. Fine. So if whenever it comes for a positive value, then you can work on it. Fine. This is the thing. Okay, now rather than busy waiting, the process can block itself. So some concepts are they have given. So spin lock, you have to remember the keyword in this particular slide. Fine. Now the next thing is deadlocks and starvation. This is also one important concept, because what you mean by deadlock and how exactly it occurs, we will see. The implementation of semaphores with a waiting queue may result in a situation where two or more processes are waiting indefinitely for an event that can be caused only by one of the waiting process. So there are some cases where, say, you are standing in a line in the post office or bank, say for example, if that is the case, and in between one customer starts bargaining, or if he starts scolding, he will waste the time actually. Because if the work is only for 5 minutes, he will get angry, that person will get angry in between, and he will start shouting, and even the employees of bank or post office will start shouting. So it will be waste of time actually. I don't know the frustration level of those, but as a person who is standing next to him, that is nothing but you, if you are waiting, then you definitely get frustrated because of their fight. The same fashion, because of one process, if other processes are waiting for longer time, that also possible. The event in question is the execution of a signal operation. When the such a state is reached, the process are said to be deadlocked. That is correct. Fine. If that is the case, if they are reaching the level where signal question in the execution of the signal operation, whatever the operation we have, or whatever the questions the sir has sent to me in a particular format, that has to be understood, or that has to be considered. Okay, that is nothing but deadlocked. We are saying that deadlocked if because of one thing, or because of other process. If one process is waiting, or if it is waiting for the execution, and it is not getting the actual path or actual platform because of other processes, then it is called deadlocked. Okay, you can see there P0 and P1, there are two processes, and it is something like wait S and wait Q. for weight S and weight Q for P0, and again for P1 it is weight Q and weight S. So in the same case for signal also, signal S, signal Q, and signal Q, signal S. It is a cross multiplication thing, isn't it? So because when you are dealing with the two processes, you should be very careful and you have to come out of a deadlock situation. Suppose that P0 executes weight S. They are giving the explanation here, and then P1 executes weight Q. When P0 executes weight Q, it must wait until P1 executes the signal Q also. Fine. So that is the one thing. So it must wait until P0 executes a signal also. Fine. So that has to be understood. Since these signal operations cannot be executed, P0 and P1 are deadlocked. Why they are deadlocked? Because you are mainly concentrating on saris and ladies wears. Gents wears are simply waiting and they are wasting time in between. I know you have this possible, this concepts are available, so you can see for P0 and P1 are deadlocked. That is the thing. Fine. Signal operation, because they cannot be executed. That is the thing. We say that a set of processes in a deadlock state when every process in the set is waiting for an event that can be caused only by another process in the set. The event with which we are mainly concerned here are resource acquisition and release. So when it has to be acquired and when it has to be released, that is the main question. Because if some processes are going for deadlock, then that means the rest of the processor will be executing, or some processors will be waiting unlimitedly. So those concepts are available when you have multiple processors running in a same machine. Fine. We say that a set of process in a deadlock, that's the same thing, right? Okay, that's okay. Another problem related to deadlocks is in unlimited blocking. That is the reason why we are saying, or starvation. So some processes may not get the resources for longer time, for the longer duration or longest duration, then it is called starvation or deadlock. Fine. So some processes may be waiting like anything, but the rest of the processes will come and they execute and they go with the most priority. And if the process have less priority, they will be keep on waiting and they will never get the resources, and that state is called starvation or deadlock. Okay. So the situation where process wait unlimitedly with the semaphore. Indefinite blocking may occur if we add and remove process from the list associated with the semaphore in LIFO order or last in first out order. If that is the case, so it is correct. It has to be maintained, or it has to be monitored. So these are some of the points which you have to remember. So you have one more concept called binary semaphores. It's a small concept. The semaphore constructs described in a previous section is commonly known as a counting semaphore, since its integer value can range over an unrestricted domain. A binary semaphore is a semaphore with an integer value that can range only between 0 and 1. In a normal semaphore case, it can go for any numbers, but with respect to binary semaphore, it can range only between 0 and 1. A binary semaphore can be simpler to implement than the counting semaphore depending on the underlying hardware architecture. So if the hardware architecture is fit and fine, then it can go for any semaphores. It may be for continuing or incrementing semaphore or continuing semaphore, or it can go for binary semaphores. But if there are any issues with respect to hardware implementation or hardware architecture, then based on the requirement or based on the capacity only, it has to choose the semaphore. So for binary semaphore, S1, S2, and you have int C1, integer variable, where initially S1 and S2 are set to 1 and 0, and the value of integer C is set to initial value counting semaphore is S. Okay, whatever the semaphore you are going to get, that has to be initialized to an integer value called C. Okay, the wait operation on the counting semaphore yes is implemented as they are just giving one code snippet. You can overlook here. You can if you don't go for it, you just have a glance over it. Okay, so it is just a C minus minus because C is initialized with the continuous semaphore, isn't it? Yes, the whatever the value of yes, it is directly initialized to C, and you are decrementing C. Fine. Now then you are checking if C is less than 0. If that is the case, then you are going for signal of S1 and wait of S2 and again signal of S1. So this is how exactly you are going to deal with it. The signal operation on the counting semaphore S can be implemented as wait of S1 if that is the case. Next, C++ you are just incrementing it. Then if you are checking whether if is C is less than or equal to 0, if that is the case, then you are going for a signal of S2, else you are going for signal of S1. Why? Because as this is a binary semaphore, the value can be ranges from 0 to 1, not more than that or not less than that. So that is the reason why you are going to check exactly how exactly the values are ranging. So this is a small concept of binary semaphore. So this will complete this particular concept. So in the next video I will be uploading that there is one algorithm, round robin algorithm. That algorithm I will upload, and some of the students have contacted me with respect to some problems of whatever the assignments I have given. So I just make a video. I will try to make a video of it, and I will try to upload it so that you can check or you can cross verify whatever the solutions you have received when you try to solve it. Fine. So let me wind up the video here. We will see in the next video. The next update will be seen in the next video. Okay, so yeah, thanks for watching.